Okay, for this question, they tell us that x has finite order in G. So we can say that the order of x is equal to n, where n is some integer. Now they want us to use the division algorithm, okay, to show that any x to the m, for any integer m in Z, is equal to one of these. So it's inside the set 1x, x squared, up to x n minus 1, okay. So we're going to show that it needs to be equal to one of those. Well, let's start out. Let's say we have x to the m. What do they tell us to use? The division algorithm. Well, let's review that. We know that if we want to divide a number m by n, we could find some quotient, q. And there will also be a remainder. Both of these will be unique, such that the remainder is greater than 0, and also less than the absolute value of the number you're dividing by, n. Okay. So this tells us that this quantity and this quantity are exactly the same. So we can just say x to the m is equal to x to the q n plus r. Okay, so that's because those two quantities are the same. Now we're going to need to make use of some properties that we proved in earlier problems. If you weren't assigned those problems and you didn't do them, or you didn't cover these properties in your lecture, make sure to do them in a lemma before you attempt this problem, because they're going to be key to solving it. We know that if we take some group element to the I plus j power, we can write that as a to the I times a to the j. Okay. So the familiar exponent law holds in any group. So we can apply that, and we can write this as x to the qn times x to the r. Okay, well, there's another law that we will be using to continue. It's also a familiar one. It holds in any group. Make sure to prove it as a lemma if you haven't seen it in lecture or proved it in a previous problem. If you have a to the I times j, well, first off, that's the same as a to the j times I. But you can write either of these as a to the I to the j, or perhaps a to the j to the I. Okay, make sure you prove these separately. And that means we can write x to the qn as x to the n to the q times x to the r. But now what do we know? Well, we knew that x has order n, so x to the n is equal to 1. So what we actually have here is 1 to the q times x to the r. But we know that 1 is the identity, so that's just equal to 1. And it will be easy to show by induction that 1 to the q will also be 1. You can try proving that. So we end up with 1 times x to the r, but again, just the identity property. We have x to the r. Now, we have exactly what we wanted to show. Why? Well, because r is some number less than n and greater than 0. So it's definitely the case that x to the r is inside the set of x to the 0 times x to the 1, and x to the 2, all the way up to x to the n minus 1. It could be any of those, because n minus 1 is the next integer less than n. So this is exactly the same as this up here. Awesome.